This is 130 pages. Okay, annual report. And I want to build a RAG system on top of it. There's so much stuff, right? I mean, imagine like, I mean, somebody wants to quickly browse through the annual report and quickly answer questions based on. This could be very, very useful solutions for investment bankers or financial analysts who look forward to a company's annual report, earnings, revenue guidance. So much of the stock markets and all that are impacted by that. No? So when some company announces something good, the markets go up, go down. So this could be a very, very useful thing that could be used by uh, by companies in a way, and also it could be very useful for even regulators, right? So especially if something is not right in the earnings report or the annual report, it could be a red flag for the regulators. Okay, so things like that. Okay, so now we want to build a RAG application on the basis of this. Oh, excuse me. So this is there are two files I've broken it up into. The first is the indexing file, and the second is the actual RAG file. The two parts we have broken it up into. So first I will take you through the indexing part. How do we do the index creation? Okay, I hope the rest of the parts are clear. I've already uploaded the slides for you. So here I just talk about the embedding. How do we do the embedding? And this is another similar example of how the whole thing looks like. Okay, so anyways, let me just take you through it now. So we need to connect to a runtime. So just during the vector DB creation, make sure that you go to runtime, change runtime type, and connect to a T4 GPU runtime. This part is important. So because Colab gives you a free virtual machine and it also gives you a free GPU machine. So change runtime type T4 GPU and connect to T4 GPU. See how it's connecting. You can all of you can just observe and then later on you can do the demo. Okay, just observe what I'm doing. So we connect to a T4 GPU runtime and you can actually see what type of runtime is given to you. We get 16 GB of GPU RAM and 13 GB of system RAM. This is a very powerful system. Okay, and it is obviously limited based on your usage. It's not like completely free. Okay, anyways. So now let me install the packages and start with the process. I will also take the Tesla zip annual reports file and upload it here. It will take a while. The one that I downloaded, I'll upload it. Okay. Okay, it is done. I think libraries are still installing. So whatever use case I'm sharing with respect to the Tesla one, you can already think of a gold mine of use cases that you can implement with RAGs. I mean, literally for personal projects, you can take any of your own personal documents. Let's say you have a resume or you have some kind of a health insurance or you have some kind of a bank statement or something. You can literally try out these ideas, whatever files I'm sharing. You can try this out on your own personal data, right? It will be very, very interesting to see. So you can take your PDF, you can replace the file name, you can take something, whatever you want. You take some of your own personal document, maybe 50, 100 pages, you have some data. You can upload that, create chunks, and you can ask questions of your document. Okay, it will be a very fun exercise to do based on our learnings. All right, I think this is still creating. Just wait for a minute. Okay, don't worry about this error. Sometimes what happens is whenever you install some packages, you will have to restart the instance. So if you get this kind of an error, what it means is you will have to restart the runtime. Okay, so go to runtime and say restart runtime. Sorry, restart session. And if you restart the session, everything would be fine. Because when you install something, you need to restart. And after you restart, don't install again. Okay, it's already installed here. This is like a machine. Okay, so if you install a software in a system, you need to restart it. That's what we did. we restarted, then we can import. See, now the error will be gone. Okay, so all good. Now we can, the zip file is also here. So we'll unzip the Tesla report file. So you can see that the Tesla reports are visible here. So we can click on it, expand it, and we can see inside it the PDF folder will be visible. Okay, so now the next part will be chunking. So we'll go and take the file and we will create chunks out of it. And we are using some generic approaches for it. And to load the PDF, we are using something called PyPDF directory loader. Okay, so PyPDF directory loader, what it does is it goes and loads the directory with PDF files. Okay, it loads the directory with PDF files. So inside a folder, there are multiple PDF files. You can have 100, 10, 100,000, whatever number of PDF files you can have in that folder. And the PyPDF directory loader will, you can just point it to a folder. See how I pointed it to the folder. I said the folder location is Tesla annual reports. This is the relative indexing, relative reference I'm doing. So inside this is my present working directory, right? Just to show you inside Colab, the PWD, the present working directory is content. So this is the current working directory. So inside the current working directory, with respect to that, I'm taking Tesla annual reports. So we're giving the entire, excuse me, the folder name. We're giving the entire folder name, and we are loading the PDF files from the folder, and we are doing chunking. This is the chunking we are doing, and you can actually see how many chunks we created. So we got the chunking takes a little time, maybe few seconds. There are many different chunkers that are there. Now what you can experiment with is you can try to chunk in different ways. So we got 351 chunks. So from that whole PDF file, we are able to get generate total 351 chunks. Okay, and now what I will do is I'll do the vector DB creation. Okay, so I'll take an open source model. So this is the open source model that we are using right now. So there's the GTE large model. Okay, so this is the open source kind of a model that we are using. A GTE large model is what we are using. Okay, so where is it? Where is this list of embedding models present? These are not LLMs, mind you. These are embedding models. So large language models were different. LLMs were different. LLMs are the the OpenAI GPT model, the Anthropic Claude model. They are different. So what we are seeing here are embedding models. Okay, so this is different actually. And you can get a list of all these embedding models from the leaderboard. So there's something called an MTEB leaderboard in Hugging Face. This is a massive text embedding leaderboard that you will find. And in this leaderboard, you will see a list of all the different embedding models. Okay, so you'll see that this is the embedding leaderboard, and you will see a list of all the top models available here. Okay, so yeah, so embedding models are different. They're not language models, but these are models that are only used to create embeddings. Embeddings are everything, not only text, images, everything. I told you like there are image embedding models also present. Okay, so can you see image and image only? So there are models that are used only for image embeddings. And look at it, domain specific. There are models that are specific for different domains, medical domain. So if you have a particular text which is in the medical field, you can create an embedding model only for that. So that because what is embedding? Embedding is just taking the text and converting it to numbers, context specific. So now the embedding models are created specific to the context. And see India specific. Indic is regional benchmark, India. And you can see excuse me, you can actually see some of these kinds of benchmarks that are available. Okay, anyways, I think we can actually see the one that we used here, the GTE large model. You can go and maybe search for it, GTE large, and you can see the GTE large model. We'll be able to see here overall. Search for it a little bit down. It might be if you come down, there it is. E5 large, GTE large. This one. It's quite a big one. Quite a big one. 335 million parameters, and see the embedding dimensions are 1024. So the model that we are using, I'll click on it. The GTE large model, it is going to take the data and it will represent the data as a vector of 1024 numbers. 1024 numbers, dimensions. Okay, that is exactly what we are using right now. Okay, GTE large is what we are using. Let me load it, and I will simply create the ChromaDB. So ChromaDB is the open source database that vector DB that we are creating. There are other open source vector DBs also that you can create. You can also use Azure vector DBs, whatever. But idea is the same. but just for the demo, I'm using ChromaDB. So this is how we are setting up the connection. So first we load uh, the embedding model. This takes a little time, and then we define the vector DB, Tesla 10K chunks. You see the Tesla collection will be created. Tesla DB will be created after a while, and then see the Tesla DB is now created, and now the embedding is happening. Based on the embedding model, we're taking all those 351 chunks, and for each of the chunks, we're converting them to the embeddings. And all that is being stored in the vector DB. That step is happening right now. This is the part that usually takes a little time. That's why I said start the GPUs, because this is the part that usually takes a little time. Because right now we only have 300 chunks, which is nothing. But if you have a bigger document going up to several hundreds of thousands to millions of chunks, this will easily take hours to even days. Okay. So now we can persist the vector DB and we can just test it out. We can just test it out with a few queries, how it works out. We're instantiating the retriever right now. So this is the retriever, and we are specifying that retrieve the top 5 similar chunks. This is where we can give the query. Okay. And just as an example, where do you see the EV sales headed in the next 10 years? Right. So, so this is the question I'm asking. And I want to retrieve the top 5 chunks with respect to the question, and see the retriever has retrieved the top 5 chunks. Okay, so this is all happening on premises. Until now, I have not made a single call to my language model. So my vector DB is on premises, and based on the question I'm asking, I'm able to retrieve the top 5 chunks. So these are the top 5 chunks that we are able to retrieve. Okay, based on the content that I have. And now what I will do, the next step will be take that retrieve chunk and send it to the take the top 5 chunks and send it to the uh, excuse me the LLM as the context. Okay. So now what I will do, so this is just my demo. So once you guys do it, what you can do is you can actually continue saving the work along with it. Okay. So now I will go to the next file, which is the retrieval part, the actual RAG part. And see, I'm actually going and saving the work here. So whatever I do here, this is the Tesla DB, right? So what I will do now, I will save my work to my Google Drive. This is a simple piece of code to save my work to my Google Drive. Because right now, what you're seeing is Colab, right? Colab is different, Google Drive is different. They are two different pieces. But what I can do is, whatever files I am taking. See, right now, if you remember initially what I did, I manually uploaded the Tesla zip file. But if you can connect to the Google Drive, you don't have to manually upload. You can directly read the files like this. So that is what I will do here. I'll establish a connectivity to my Google Drive. You can just run this code. All this notebook is given to you. So you'll get an option to enable the permissions. You can check all the permissions, permission for all the 8 services. So this is like where you're giving Google permission to access, Colab, the Google Colab permission to access your Google Drive. And once you do that, you can see my drive will be mounted. Okay, if I refresh, you will see I will have my Google Drive mounted. This is my personal Google Drive. And within that, I will see all the files. All my personal files will be there in my Google Drive. And what I want to do, I want to copy the Tesla DB folder, whatever the Tesla DB folder I have. Can you see? I want to copy the Tesla DB folder in my current working directory to my this one, Google content drive, my drive, AI Gen AI training. You want to see that? I can show you from here. So content drive, my drive, you can see right now. So I'm actually saving this here. So I want to take the Tesla DB folder from here. So I want to save it in content drive, my drive. So this will take you to my drive. That is my Google Drive. Within that, I have a folder called AI Gen AI training main. Within that, generative models. Within that RAG, within that Tesla demo. So within that RAG, within that Tesla demo, you can see the full thing. And within that, I want to save this. Right? I already did that before. But if you run this code, it will just overwrite. See, it is going to save it now. Now we will go ahead and effectively go to the next notebook, where we will simply load the vector DB and do the RAG. This is the next part of the demo that we will have. So we'll simply load the vector DB and do our RAG part here. Okay, so that's the next part that we will do. Okay. Now, once again, this is a different VM, and here you don't need a GPU because uh, all the processing here will happen in my GPT model. Okay. Using the GPT model, you don't need to use GPUs. Okay. Because remember, the GPT model is hosted in Azure servers, or if you're accessing through OpenAI, it is hosted in OpenAI servers. So you don't need too much of compute just to access those models. Okay, so those models can be accessed relatively in a simple way. You don't need to use too much of compute to access those models. Not much of compute is required. Anyways, I'm just installing the packages once again. Remember, the first part is done. The vector DB creation is done. You can see my vector DB is already available here. This is what I wanted to show you. So this is my vector DB. It's all available now. Okay, it's all available now. You can see it's modified today. It's all available now. And now I'm just going to use that vector DB. Given a new query, now I will set the I will retrieve the chunks and give it to my language model and get a more refined response. Because right now the response was not refined. I was just getting those 5 chunks randomly. Now the LLM will give me a refined response. So we were able to run this. This is the same Azure API key which we said yesterday. This will work fine for everybody. In fact, you can all run this notebook after this demo. So I'll give you time to do that. This is the same stuff. This will run the same way. Load the vector DB. Mind you, we already have the vector DB saved in my location, my Google Drive location. So this is a new VM, right? This was a different VM. This is a different VM. Every time you start a new Colab instance, this is a different VM. This is a different VM. So my files and stuff is not present here, mind you. Okay, so this is a different virtual machine. So I have to make sure that I get my Tesla DB here. So I will load my Tesla DB from my Google Drive. So I already have it in my Google Drive, right? So I will load it from here onto my VM, right? So let's do that. So first I will connect my Colab to my Google Drive. This is in the new VM, mind you. It's a different machine. So I'll establish the connectivity so that my Colab can talk to my drive. Because mind you, Colab is very sensitive. You can write Python code, and literally you can you can modify, delete, read files. It's very sensitive actually. That's why Colab asks for permissions to ensure that whatever code you run, you are granting it permissions to see and like change your files because it is literally working, interacting with your drive file system. Okay, so once I do this, you can see the Tesla DB will be visible on the left hand side. And you can see it's available here. Just in case people are doing the demo, I just gave you one more way to work it out. In case you think the Google Drive upload, download is too much to take for people, what you can do is I've also given the Tesla DB zip file. I mean, if you think this is difficult or, like, anyways, it's not very hard, I'll guide you. But in case you don't want to do this Google Drive way, you can just download my Tesla DB zip. You can download it and you can just go here and drag and drop it, upload it. That's it. And you can just run this command. I've right now commented it, but you can just run this command. It'll give you the same Tesla DB folder. My objective is to get the Tesla DB folder. Here you created it, and here you want to use it. That's it. They're two separate setups. Okay. So now we define the retriever the same way we define the retriever, top 5 chunks. And now this is the system message for the LLM. Okay, so you can clearly see we are saying that you're an assistant to a financial services firm. This is the exact use case that we were discussing, who answers users' queries on financial reports. So given the financial report, somebody can quickly query, they can get answers to questions so that analysts can make investment decisions based on the real-time financial reports of companies. And remember, friends, here we are just looking at a single company's financial report, Tesla. But a very, very powerful solution would be you can take all the top 500 companies in the BSE Sensex, the top 500 market capitalization companies, and you can take all their financial reports from the last 10 years. That could be a very powerful solution. And it's not very hard. All this is publicly information. All the publicly traded companies, they publish their annual reports. You will have to scrape the data. Just take all the annual reports from the last 10 years. You can save all that data in a folder, and you can build a retrieval augmented generate RAG system, with respect to all the last 10 years uh, financial financial data. Okay, so anybody can ask any question based on any company, and the RAG system will be able to give you answers. It could be very, very powerful idea actually. So anyways, one very important thing is user input will have the context required by you to answer the user questions. And you can see the context will begin with the token hash 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 context. This is a retrieve context. And the context contains references to the specific portions of a document relevant to the user query. So this the context is the one that is retrieved from the vector DB. So you're already telling the LLM that, hey, uh, when you get a question, don't answer the question based on your knowledge. Please answer the question based on the context that we are retrieving. And this is a very, very important aspect of a RAG system. In a RAG system, we don't want to answer questions based on we don't want the LLM to use its own internal knowledge to answer the questions, but we want the LLM to look at what context is retrieved, and based on the retrieved context, we want it to answer the questions. That is the idea. You can see we're explicitly saying that please answer the questions only using the context provided. Do not mention anything about the context in your final answer, and your response should only contain the answer to the question. This is the part where you're further highlighting the privacy and confidentiality of your documents. So the end users will never get to know the complete document. So this is again very important, right? So you don't want the end users to get to see parts of the document. So only based on the question, the only the answer will be given, but the chunks will not be provided. The context will not be provided in the final answer. Okay. And if the answer is not found in the context, please say, I don't know. This is also important because the GPT-4o model is very powerful. It will do whatever it takes to answer the questions. Even if you ask it a general question, it will still say, okay, maybe this, maybe that. It will give you some generic answers. But you are very explicitly stating that if the answer is not in the context, please say, I don't know. You're explicitly specifying that. This is the user message template you can see. And now we just test out the RAG system. What is the annual revenue of the company? So first we will retrieve the top 5 chunks. Okay. And this is the top 5 chunks you can see. And now we can compose the response, user input. And this is the LLM call that we are doing. And we can test it out. It takes a minute and says annual revenue of the company is this. This is the part how the RAG system is working. The last part was easy. The last part is what we have been doing already for the last 2 days now. Okay. So once we have the user query, we go to the vector DB. We go to the vector DB. We retrieve the top 5 chunks from the vector DB. And we send the original user question. See, this is the part where we are doing that. We send the original user question and the retrieve chunks as part of the user message, and we get the response. Okay, and this is the final GPT response. It's a much cleaner response. We're not getting those chunks and all those random text that we were seeing before, but now we're getting a very refined answer as we're able to see. Okay, so this is the way how we design RAG systems. The last part is where I will talk a little bit about evaluating a RAG system. Very briefly, I will talk about it. Evaluation part is also very important. So all this while we discussed about how to build a RAG system, but how do we evaluate a RAG system? And there are usually two strategies that are used for evaluation. One is called groundedness, one is called relevance. Now, before that, I want to clarify, there is no ground truth. There is absolutely no ground truth in these kinds of use cases. So here we will use a judge model. So there is no ground truth that we have here. We will use a judge model to evaluate this particular model. So judge model is what will be ultimately used. So what is groundedness? Groundedness means, is the response supported by the retrieved context? So whatever you're responding, is that supported by the context that is retrieved? So the response should not be something random. Whatever answer you are giving, that answer should be based on the context that is retrieved. Very important. Okay. Whatever answer you're giving, the answer should be based on the retrieved context. That is what we refer to as groundedness. The answer should be based on the retrieved context. And this is important because, as I told you, the large language models are very powerful. If you ask it any question, the language models will still do whatever it takes to generate an answer. But that is not what we want. We don't want them to just generate some random answer. Excuse me. We want them to go and answer only based on what they know, not just generate some random answer. So groundedness is an important parameter, and we will use a judge model to evaluate whether the responses are coming from the context and not from somewhere else. And another evaluation metric is something called relevance. So relevance is going to tell you, are we even answering the question? That's also important, right? So you're asking some question and the model will give an answer. Are we even answering that question? So you are saying, okay, what is the annual revenue of Tesla? And the answer is, okay, the profits are this. That is not what I asked. I asked you about the revenue, not the profits. So relevance will do that. How do we do that? We use two judge models. We use LLM1, LLM2. This is the judge model that we use to evaluate. So the first part is we go and use the first language model to generate the response, and we use the second language model, the judge model, to evaluate that response in terms of groundedness and relevance. And that is exactly what we are doing in the last part of our solution. If you see, once we get that final response, we are defining the judge models. This is the same approach that we followed before, right? So these are two judge models, right? So we define the groundedness rater uh, model, and we define the relevance rater model. And this will usually be two separate models, two separate judges, each with its own system message. So we have a separate system message for the groundedness judge and a separate system message for the relevance judge, obviously, because they are meant to do two different things. The two separate system messages, and you can see what will the judge get as input? The question, the original question that was asked, the context that was retrieved, and the final answer that was given. So three components. First, you have the judge model. The judge will have a system message. Let's say this is the groundedness judge. So the groundedness judge will have a groundedness system message. This is the user message. As part of the user message, we will have the question, the context, and the answer. What was the original question asked? What was the context that was retrieved? Excuse me. And what was the final answer that was given? This will be part of the user message. And you can test it out based on the question. First, the chunks are retrieved. The final answer is given. And now you will send that whole thing to the judge. Can you see? Look at this. This is the groundedness prompt, what the judge will see. So this is the prompt for the judge. Role system message, the system message for the groundedness judge, and role user message. And as part of the user message, see what we have. We have the context. The question, hashtag question. This is the question. Then we have the retrieved context. And then if you come all the way here with the final answer, the final answer actually starts from here, the answer. So this is all part of the user message. The system message is the original system message for the judge, and the user message is basically a combination of the question, the retrieved context, and the answer that was given, the hashtag answer. This is where it's starting from. Answer. The annual revenue was so and so. And you can see the judge model is giving a 5-star because I think the metric was completely followed, and the AI's answer is accurate, directly derived from the context. And it does not include any external or fabricated information. This part is very important because a RAG system must answer questions based on the context, based on my company's data for accuracy. The accuracy part is very important. You just don't want the LLM to answer the question, but it also has to be accurate based on my company data, not based on GPT's own understanding. Okay, so this is how we look at a complete end-to-end use case of a RAG system.